Hello, everybody, and welcome to today's Lean-In session. I'm Michael Linke, and on behalf of the Australian Institute of Architects, it's great to have you with me yet again. In today's session, Timo Bleeker is the Director of Idealings Architecture, and he's joining me, and he'll be covering the fundamentals of the Passive House Standard, and he'll be discussing the importance of introducing the principles at the very early stages of planning. Timo is also going to delve further into how the Passive House Standard can maximise building performance and also benefit the well-being of occupants in the property. Timo is going to feature case studies and affordability research in a side-by-side comparison between conventional builds and passive house builds as well. Don't forget that today's session is being recorded, and as always, that recording will be live later on tonight on our dedicated COVID-19 Lean-In recordings page as well. Also, don't forget that the chat box at the bottom is your friend today. So if you have any questions at all for Timo, don't forget to just pop your questions in there, and then time permitting, I'll go through those with Timo at the end of the session as well. A little bit about Timo. Timo Bleeker is a registered architect. He's a project management professional, Green Star associate, and a passive house designer. And Timo has worked as a design and project architect as well as contract manager on small to mid-scale construction projects. And in September 2019, he became a director of Idealings Architecture and then really started his further pursuit for passive house-based solutions. And it's great to have him on the program. He joins me now from Perth. Timo Bleeker, welcome to today's program. How are you?
Thank you, I'm very well. Thank you for introducing me and giving me the opportunity to talk to you today. I just add a quick word to myself and then touch on the topics we'll cover today. And I've got a little quick question for yourselves, basically, and then we carry on into the presentation. So just a quick word. I've lived in Germany for about 30 years and worked there for 5 years before coming to Australia. And once we arrived here, we were sort of surprised and wonder that temperatures, indoor climates inside the houses in winter can be quite cold and in summer can be quite warm. So that made us, driving to our passion and saying it's like, oh, we want to get people into more comfortable living spaces. We don't need to have cold homes or too hot homes or too cold homes anymore. And we want to provide education to the public out there to get the people into a situation where they can do informed decisions about their future homes and their future buildings or the design. So basically tackle the unknown out there. So what we cover today is introduce the concept of a passive house and try to understand the 5 principles. We'll be looking into the criteria that passive house gets measured against. There are a couple of more elements that passive house needs to adhere to, but we concentrate for now to keep it simple for the 5 main criteria. We discover the benefits of passive house in Australia, and we look into how passive house professionals can give support and consider passive house in Australia. But as I said before, we dive into the presentation any further, I'd just like to ask a question to you guys out there to get a bit of an idea who the audience is and where you are from, basically. So Kat, if you could just do that. Thank you. Just maybe give it about sort of 10 seconds, 10, 15 seconds for everyone to go through it and maybe choose something that applies best to you. So basically, are you an architect? Is your background rather a passive house designer, engineer, developer, or other environmental professional? Are you coming rather from the trades or builder side of things, or are you not related to the construction industry at all? or are you a private person that is keen to build soon? Maybe give it another second, yeah. Oh, the dominant here is in the architect section. So about 90% here, but we've got some people from the non-construction industry and someone is also keen to build. Thank you for that, and yeah, welcome to the presentation. And nice that you are all joining. All right, let's carry on. What is passive house? Passive house, let's have a look at some facts first. So conventional houses in Australia often are losing a lot of energy due to their poor build and rely on active heating and cooling that are based on powered by fossil fuels that add to Australia's greenhouse gas emissions. Let's have a look at the principle of a flask. A flask is a solution to keep coffee or teas warm, or any drinks that you might like, without using any active energy. A coffee machine, on the other side, needs active energy to keep the coffee warm. So passive house, you can sort of imagine it being similar. It has, and it wants to have outer envelope that basically insulates the interior and keeps the energy that we apply to it inside without much further active energy. I always remember the quote of a former colleague of mine I worked with for a while. He was saying, let's all live in a thermos flask and then we are all good. not quite like that, but it's somewhat like that. Passive house is a solution that is applicable to buildings of all classes. So it's not just class 1 residential buildings. It applies to all class 1 to 10. So you can even do your shed in the backyard if you have a bit of a workshop there as a passive house if you want. So it applies to everything, to schools, to hospitals, to office buildings, you name it. Passive house is a building standard that got developed by the Passive House Institute in Germany about 30 years ago. I think the first passive house building was around the 1988 or 1990s, and it exists still then. Passive house is a construction concept that provides energy efficiency, a healthy indoor environment, comfortable indoor climate and temperature between 20 and 25 degrees Celsius. So it's stable indoor comfort, and it's affordable to build. Regarding the affordability, I come to that a bit later. But let's also remember the indoor temperature, 20 to 25 degrees. Passive house wants and does guarantee or aim for this temperature range. Before we look further into the passive house principles, let's have a look at the terminology for a second, because there's often quite a confusion between solar passive and passive house. Solar passive has a core principles to it. I'm just looking at the four main ones here, which is orientation, natural ventilation, shading, and thermal mass. Where passive house does take that into consideration as well, but they lay a lot of emphasis on the building envelope and on the fresh air, 24/7 fresh air supply. You might know, say, the natural ventilation and the fresh air might be somewhat the same. It's not quite, because natural ventilation depends on the occupant actively opening windows and doors to actually leave fresh air in, or what we often find is louvers that are permanently open or operable to get air in to get fresh air. So, but what about those days where it's too hot and too cold, or where we have situations where we don't want that outside air to come in? That's where the fresh air supply of the passive house principles come into play. But we look into that a little bit further down the track. The 5 principles at a glance. The first one is continuous insulation. So we need proper insulation to avoid wastage of cooling and heating energy to the ambient outside air. And it needs to be a constant layer all around. High performance windows. Those windows there are often the weak spot in the envelope, but we can't just treat them like holes in the wall. These windows still need to have a performing value to it. So we need to address that, so these windows add to the continuous insulation layer. Airtightness, to prevent the moist that sits in the indoor air getting into the structure and create damage to the building structure, and to avoid getting unwanted and uncontrolled air in from outside, so getting drafts, etc. No thermal bridges, to avoid health issues for the occupants, and avoid gaps in the outer envelope where the cold could come in and provide cold surface temperatures and condensation and mold issues. And the fifth and last principle is heat recovery ventilation, which is often called the lung of the passive house. But let's look at all of those principles one by one, starting with the insulation. Some facts at the beginning. A lot of Australia's building stock are only partial or insufficient insulated, with high U values 2 watt per square meter Kelvin and above. And they often have a non-continuous insulation. So basically insulation stop-starts, and we have gaps, for example, in wall to roof joints and other corners. So what that means is the higher the U value is, the more heat flow goes through a wall, and the lower it is, the less goes through it. It's a pretty simple principle that's probably easy to understand. So we want the insulation installed as a continuous layer, as highlighted before. So that yellow line here needs to be continuous, even in the tricky bits where the roof meets the wall or the roof cappings or at the footings, etc. So we want to look at those details that achieve a continuous layer. With low values, U values as low as 0.3 watt per square meter in Kelvin. Mind you, that's for Perth. In other cities or other locations, that might be a different value. In colder climates, sometimes underslab insulation is needed, as you can see at the yellow dotted line here, especially maybe the Melbourne and Tasmania region, certainly the northern European region. We usually have underslab insulation. And keeping the heat in and keeping the heat out works in both directions, obviously. In winter, the insulation keeps the heat in, and in summer, it keeps the heat out where we want it. Or look at it the other way around. In summer, the air-conditioned air stays inside. The second principle is high-performing windows. So no single pane or laminated glass can achieve a thermal transmittance performance required to avoid energy wastage. Why is that? Because I don't have an insulation layer. It's basically just a pane of glass or 2 panes of glass that are laminated to each other that doesn't have an insulating capacity to it. So it's just the thicker the glass becomes, it might take a little bit longer for the heat to go from one side to the other side, but it's basically just a material that conducts heat. Remember, we don't want those windows just be holes in the wall. They need to have a thermal performance to it to close the loop of the thermal insulation. So what we want is the windows must have a double glazing to it, because the cavity in between is the insulating bit and has usually a gas infill, and that gas has a thermal property. So that's basically the main element that thermally insulates the window or the glazing. And this yellow and red highlighted bits basically need to be a continuation of that outer layer of that yellow line that we've seen before. It needs to meet the wall insulation at the top of the window and needs to meet the wall insulation at the bottom of the window. So with a single pane glazing, this won't be achieved because there is no insulation there. So we need that gas infill, so minimum double glazing, plus low conductivity spacers. The spacers are the ones that keep the 2 glass panes apart, and thermally broken frames, or even insulated frames. So all those yellow highlighted bits there are the insulated or thermally performing elements. If you've got a thermally unbroken frame, as we often find with aluminium frames, then you've got basically a thermal bridge there, where the inner surface gets really cold in winter and hot in summer, and you lose energy there. Third principle, airtightness. Currently, a typical Australian home has around 15 air exchanges per hour. What does that mean? That means that every 4 minutes, the entire air volume of a building is completely exchanged. I repeat that. Every 4 minutes, the entire air volume of that building is completely exchanged, and with it, also the cooled and heat air or energy that we just applied to it. How do we measure that? Airtightness is measured at 50 Pascal. That means there's a pressure difference that is about 17, that simulates a situation that is around 17 knots or 20 miles per hour. This is, just to picture it, a situation where small tree leaves or branches start to sway a little bit, or where waves on the ocean start to get those little white crests, but just the start of it. So it's a pretty common weather situation. Under this gets measured, and under this situation, a current typical, excuse me, a current typical home has 15 air exchanges per hour, so every 4 minutes. Passive house wants 0.6, so that means every 1 hour 40 minutes, the entire volume is exchanged instead of 4 minutes that we are facing here. Just a quick quote from Green Star Council CEO Davina Rooney. They released about 2 weeks ago the Future Home Strategy, and I'd just like to quickly read that here, reading that together with you. So airtightness is the reason of 25% of heat loss, and it's estimated to be caused by droughts. So good insulation, when combined with airtightness, can save homes up to 40% in energy bills every year. I'll just leave this statement as it is, for now, and come back to that home strategy a little bit later again. So we want to avoid leaky buildings and uncontrolled ventilation, as you can see here on the right. So leaks can be everywhere, basically, around the windows, air vents, exhaust fans, your power switches, your power points, etc., etc. So this is uncontrolled ventilation, where also drafts occur. We want to plan the airtightness layer, which you can see here in the red line, all around the building, and to avoid penetrating this layer. The airtightness layer in our local areas here, I'd say, excuse me, Perth, Sydney, Melbourne, Tasmania, climate should or must be on the inside of the insulation. In more tropical areas, it might be the other way around and needs to be looked at in case-to-case basis. But let's, for simplicity, just say it needs to be on the inside of the insulation layer. So that therefore you need to avoid penetrating this layer and want to plan where you need to penetrate it for services, etc., or how it comes together on joint details like wall to roof or wall to floor details, etc. The fourth principle is avoiding thermal bridges. Thermal bridges are like windows, the weaknesses in the building envelope. They waste heating and cooling energy. They can create condensation issues and mold buildup. And these mold buildups are a health issue, so they can create allergy and asthma problems. On the left-hand side picture here, these are thermal images that we've done in our house. You can see under the window there a spot where the insulation bed might have gotten wet or is a bit wrongly installed and doesn't cover the bottom really. So there's the thermal bridge, and that's a location where the cold or the heat escapes and where the inner surface gets colder than the remaining. So you can see it's around 17.7 degrees there, colder than the remaining areas. The middle picture there, aluminium framing, measuring the temperature of it in winter time, was 11 degrees at that time. This is a situation where you get condensation for sure on the inner side. And if it gets even colder, then mold creates, as you can see on the right-hand side there. It's also our house. We gotta clean that up every winter time because the aluminium framing there gets too cold, and the dots that you see there is not just dust, this is mold. And by the way, this is a residential class 1 building built to NatHERS 6-star requirements. So what do we want to do? We want to avoid gaps in the thermal envelope, and we want to avoid penetrating this with highly conductive materials like steel, aluminium, concrete, and so forth. On the right bottom side there, you can see probably the most typical thermal bridge in suspended concrete ceiling construction, where the slab is just sticking out through the external wall and creates a huge thermal bridge where the heat can just escape. And on the right of it is, because I've got this picture from a German webpage, is a solution that often got applied in Germany. Is basically cutting off the slab there, apply insulation to the outside face, and install a new balcony, self-supported, in front of it. Heat recovery ventilation. Now that we applied airtightness to our building, how do we maintain ventilating the building? First, I want to say heat recovery ventilation and airtightness often gets misunderstood. It doesn't mean you are living in a hermetically sealed box. You can still open your windows as often as you want and as long as you want to let fresh air in. We strongly encourage that. But as mentioned earlier, what about the days where it's very hot outside or very cold outside, or there are situations where you don't want the windows open? Or imagine a situation in our busy lives, we sometimes forget to just open the windows because we're just forgetting it. So we want sort of a solution there that still provides us with new fresh air in those situations. I always remember here a situation where I've been at a presentation. There was still a face-to-face presentation, good old times, where we've been in a fairly big room with high ceilings. There were probably about 25 to 30 people around. And the presenter had a carbon dioxide sensor, a mobile one, and put it on the table there and measured at the beginning of the presentation. And it showed 400 ppm, which is pretty good, excellent air rate there. Then he presented about an hour, maybe 1.5. And we looked at the sensor again after that presentation, and it showed 1800. At 1800, you can see it says bad. Ventilation strongly required. So what I want to say here is basically while we are in the buildings, the CO2 values are going up when we are not insulating or open the windows. Sorry, when we're not opening the windows or ventilating. So we need to address that. So what do we want to do? A solution is a heat recovery ventilation system. What does that do? It supplies fresh air to primary rooms like bedrooms, living rooms, dining rooms, etc. Then it meanders through the building and warms up. Let's just imagine it's winter time, and it warms up as it meanders through the building because of cooking or computers that are on or showering, etc., etc. So the air warms up and gets extracted in the kitchen and bathrooms where we've got doors anyway, and directed back to that unit you see there in the basement that we call the magic box. In the magic box, there's just a little fan that draws about 30, 40, 50 watts maybe. that operates basically this system. So it's less than a conventional light bulb of active energy that this system uses to get air into your building and out of your building. Then, excuse me, then what happens in this magic box? In this magic box, the warmer exhaust air passes the colder fresh air that comes from outside. They don't mix, they just pass each other, and they're separated by a little thin membrane. And what happens there is that the energy that is in the warm exhaust air gets transferred through the thin membrane onto the fresh air. Basically, the energy that sits in the warm air gets recycled and put into the fresh air without any active energy apply needed. So it's recycling air. It's recycling energy basically. And the efficiency of those systems, they go up now sort of 92–95%. So you can just imagine for simplicity. It doesn't just quite work like that. I just want to give an example so it's better understood. It doesn't work one-to-one like that. But let's imagine internally we've got 23 degrees and we've got degrees outside. 92% of the 23 degrees gives us about 21 degrees. And then the Passive House Institute sort of takes a percentage off just a generic value because of installation gaps, etc., to allow for this. It gets reduced by 10–12%, so that gives us an air temperature of around 18%. So the energy of this 18 degree air gets transferred to the 5 degree air that comes from outside. So just adding 18 and 5, we are back at our 23 degrees internal temperature. So in this very simplified scenario, we wouldn't need any active heating at all to get back to our temperature. As I said, it's not just if a building physician now would talk to me, he would say, it's like, oh, it doesn't quite work like this, but to just, simplify it down for us, this is in simple words how it works. But for the efficiency to work, we need air tightness of minimum 3 air exchanges per hour. Otherwise, the efficiency drops by quite a bit, and you start heating again and apply dollars to heating and cooling. So this heat recovery ventilation unit basically is the lung of our passive house. So here we can see that up to 92%, I think 95 nowadays, recovery efficiency if we get the air tightness. So looking at the 5 passive house criteria. So this this little fan that draws 30 or 40 watt is within those heating and cooling demands of less than 15 kilowatt hours per square and anno. Requirement for passive house certification. The same applies for the cooling demand. We are looking at a frequency of overheating less than 10%. I'll get into that in a second. And we're looking at air tightness of less than 0.6 air exchanges per hour, which means your volume of air internally gets exchanged every 1 hour 40 instead of 4 minutes. You find nowadays quite a bit. And Passive House introduced a renewable primary energy that covers basically the remainder of the electrical usage of the building, not only the heating and cooling demand that you see on the top there, but the energy demand of the entire building you need to use for running your laptop, for cooking, etc., etc. And Passive House wants to use renewable energies and steer away from gas or from fossil fuels. Quickly back to overheating. To understand that principle a little bit better, I'm just going through a simple calculation here. There are 8,760 hours in the year, and 10% of it are 876 hours. Assuming here in Australia, we might have 8-month period in spring, in summer, and in autumn. we can divide that by this 8 and get 110 hours per month of overheating. Dividing that by 30 days in a month, we get about 3.5 hours per day in those 8 months where the temperature would be above 25 degrees. And remember, at the beginning we said we want to achieve an indoor comfort of around 20 to 25 degrees as a temperature range. So the frequency of overheating, where it goes above this 25 degrees, we want to keep that lower than 10% to achieve Passive House certification. Personally, I would like to have it less than 5 or even 3%. So then you would just have an hour or 1.5. When you've got 3%, maybe 1.5 hours per day in those 8 months that it's above 25. Looking at this primary energy renewables quickly, I said that already, no fossil fuel generated energy, and this renewable energy needs to cover the building's total energy consumption, and that needs to be less than the 60 kilowatt hours per square meter per year. So you can now have a look at your personal bill and the kilowatt hours used there, and compare a little bit. It would probably be quite a bit higher, but it's achievable. We'll know that it's achievable. Now, Passive House planning package is a tool that we designers use to know and measure that the Passive House criteria are met. I don't want to dive into these numbers here. I just want to show there's a tool that shows basically where on the building you lose and gain heat, and it can show how much. So which part of the wall, which part of the window, which side, which part of the roof gains or loses how much heat through it. And it's a modeling software developed by the Passive House Institute with aid of dynamic simulation tools. So it's based on the data pool of all the buildings they have during those last 25 years, and it's pretty accurate. So the heating and cooling demand is then basically the gap that you need to make up because of those losses that this software can show you. And when you know where the losses are, you can basically address them in your design, in your concept design, in your design development, by reducing, for example, window sizes, or provide more shading, or relocate some windows to a different spot to get a better performance. Little case study on NatHERS 6 residents here in Western Australia, class 1. It's our own building, apparently, our own building, by the way. So there are quite a few numbers. I don't want to dive into the numbers too much, but I want to explain what this means. So on the left-hand side, you see the first column, which is fairly low. That's the original design. And we're not the biggest heaters or air conditioner users, so we rather put a jacket or a sweatshirt on than using our air conditioning. But what does it mean is we accept any indoor temperature that there comes. We measured that throughout the year. We measured anything between 13.5 and 34 degrees internal temperature. That's not comfortable. It's not healthy either. So this building doesn't have a comfortable, stable indoor temperature and indoor environment. Now we simulated this and applied Passive House principles to it. So if we would heat and cool to get it into the Passive House temperature range of 20 to 25 degrees, we would need to apply 130 kilowatt hours per square meter a year to get it to those temperatures. And we also know, because they're only single pane glazing in here, etc., we lose it straight away. So it's just constantly running and applying a lot of kilowatt hours. What we then did is applying certain steps to get it further and further and further and further to the Passive House principles. So applying better insulation, thermal mass, maximize the solar gain, improve the glazing or the windows, add airtightness to the building, add ventilation, heat recovery ventilation to the building, and so forth. So on the right-hand side, then after applying all those steps, we got to our internal temperature comfort, while only applying minimal kilowatt hours per square meter and year to the building. So this is basically what the PHPP, the Passive House Planning package, can do. It can show all the steps that you apply throughout and how good you get. So when you get a client, and we got clients, quite a few clients, that wanted to be energy efficient, not necessarily wanting to go all the way to passive house, but want to be energy efficient. But the question then was, how much energy efficiency can they get for the dollars they have? So with this sort of stepping approach, you can give them a couple of puzzle pieces, while a builder or QS puts a dollar number to it, and they can then weigh up what they can afford, how far they go, and are put into a position where they can do an informed decision about those elements. So maybe they spend rather $1 on this than on the fancy tile, because they can do that later, kind of thing. So it gives them more visibility of what they actually get in terms of thermal performance to their building. So PHPP can visualize all this. There's some dependency on a couple of those steps that you need to do together, but others are not. So that can be explained to the client. Another case study that the Green Star Council has done together with the Australian Passive House Association on a Class 2 multi-residential building. It basically shows how much energy or it is multi-residential Class 2 on 300 plus dwellings, I need to say. And it shows basically how much natural gas and electricity energy these dwellings use under the Green Star scheme, which is the blue and the gray columns here, in comparison how much it would have used under the passive house scheme, which is the green line here. So you can see that it's quite a bit lower. I mean, the aggressive Green Star scheme is already quite sustainable. Still, the passive house principles are still a lot lower than the Green Star. Sorry. For more information, I recommend looking at these documents available on the Green Star webpage. Now, we did a cost comparison between the passive house and the conventional house. And the conventional house is Class 1 residential, built to NatHERS 6-star. And we applied a couple of parameters and assumptions to it. So to get the building, the NatHERS 6-star building, to the 20 and 25 degree comfort, we assumed 100 kilowatt hours per square meter and year on energy that is needed to get it there. And we also assumed increased project cost of about 10%, reduced heating and cooling demand for the passive house of 75%, and electricity demand of 18 kilowatt hours per square meter and year for the remainder of the energy. That's a value that the PHPP gave us. An electricity cost of 27 cents, inflation 1%, and a loan interest of 5% over 30 years, which is quite conservative, as we know, but we kept it there for now. Now on the left, you see the NatHERS 6-star building. On the right, you see the passive house building. And because the NatHERS 6-star building has pretty high operational costs, which is the heating and cooling in blue and the other electricity in yellow, the passive house, because of his low operational costs, but additional 10% cost, are still quite cost equivalents from day one, from the beginning. So in the first year, for the NatHERS 6 building, you would have annual costs of, let's say, a little higher than $4,000 on heating, cooling, and other electricity. On the passive house, you might have just slightly more, maybe 4,300 or something, including that additional cost of 10%. So where do these 10% come from? I'll get into that in a second. But what we can see here is that the passive house might not need to be that much more expensive than NatHERS 6-star building built to rock bottom regulations, basically, just because of their low operational costs. At a stage where the loan is completed, you get that amortization point after sort of 30 years, where the passive house gets cheaper because of their low operational cost. Just highlighting an option here, if those additional costs can be paid up front without a loan, for some projects that might be an option, the amortization point is reached even quicker after sort of 15, 16 years. And due to the low operational costs, that's a lot lower than the NatHERS 6-star building. So those additional costs, what are the drivers? We and other professionals, they've seen four main categories in drivers for those costs, which are material availability and cost, design knowledge and construction knowledge in the industry, and building design complexity. So building design complexity, the more complex the building gets, or the less complex it gets, the less costly it is, which is a principle that we might all understand. But also, what's the baseline for comparison? When you compare it to NatHERS 6, yeah, there's a cost premium to it, but it's like buying a dishwasher that is rather silent. You pay probably a little cost premium as well as the standard that's a little bit louder. But if you have a client that already considers some energy efficient design principles in there, let's say solar passive principles, etc., the step to passive house might not be as big anymore. So the saying that passive house is always too expensive might not be true there. The cost premium for passive house might not be as high. So what have we learned so far now? With passive house, we get improved health by avoiding thermal bridges and achieve less risk of mold problems. We achieve improved comfort through heat recovery ventilation, achieving a constant indoor environment between 20 and 25 degrees. We achieve durability through airtightness and less risk of damaged construction. We achieve energy efficiency through insulation and double glazed windows and don't waste as much heating and cooling energy anymore. And we've learned that it can be affordable because it's affordable from the beginning. Now, quickly looking at some passive houses worldwide. They mainly cluster around Europe, Northern America, East Asia, New Zealand, and now it starts here in Australia. But why hasn't that been picked up in Australia before? One item that we experience is the unknown. So passive house principles are basically not known amongst owners or future builders or a private person that want to build. Misinformation, for example, about airtightness and recovery ventilation, thinking, oh, that's all a sealed box, or even getting comments like, oh, in our climate, we only need double brick and single pane glazing. That's enough insulation. We don't need more. Confusion about solar passive principles and passive house, as we outlined at the beginning. Materiality, availability, and cost. Construction design knowledge in the industry, and the mindset of short-term investment. So passive house is a bit of a long-term, or is a principle where you get your benefits long-term, So if a client wants to sort of invest in a building and then sell it after 5 or 10 years, they might not want to go through this little additional cost. These 5 elements we tackle through some education and spread the word, and actually say, yeah, passive houses out there, and it can be an option for you. Material availability and cost and construction knowledge gets tackled for the last 2-3 years quite well through training. And we feel, or we see that the demand for energy efficient buildings is rising, and that also gets picked up by the industry, getting more affordable materials into the market. Short-term investment, there's an incentive out there, for example, from the Bank Australia, lowering interest rates for energy efficient buildings. So that could be something to tackle the mindset. So how can professionals assist in getting a passive house done? Certainly a certified passive house designer needs to assist and do the assessment and do the advisory. Certified passive house trades are recommended to consider builders for certified staff. It makes it easier on site and more cost efficient to actually build the house. If you want to go for certification, a passive house certifier is needed to assess the design, and obviously the materials and certified components are required. Reliable and proven tools are helping to plan and optimize this, which is a passive house planning package, PHIPP, and the related design PH modeling tool. And us as Idealings Architecture, we provide those services. Standard architectural design services from concept design to contract administration. We do the passive house consultancy when there's an existing design that architects might have. We can assist and advise on passive house principles. We do the PHIPP. We can advise on acknowledging the passive house principles in the Green Star scheme. We do airtightness testing, HRV commissioning, and education such as presentations such as this. Let's have a look at the passive house consultancy for a second. To achieve a maximum energy efficient building, we recommend getting advisory and a passive house planning package done early in the design phase to avoid replanning things later on, because it can have quite a substantial effect on the design when you need to move or want to move windows or add some shading elements, etc., etc. So you certainly want to include a passive house professional before a design goes to a DA application. Further, we can assist in the contract documentation and the tender process, and even do some advisory on site to builders that are not quite yet knowledgeable in the passive house construction. I want to finish the presentation with 2 slides of the Green Star Council doing a partnership with the Australian Passive House Association. Because by following the passive house principles, 30 points get acknowledged in the Green Star scheme. That is basically almost 1/3 of all available 100 points, and it's 2/3 of the minimum 45 points you need for the 4-star rating. So while following the passive house principles, a lot of Green Star points or boxes already get ticked. And secondly, I want to come back to this future home strategy that the Green Star Council released about 2 weeks ago, which is aimed for the residential sector. And this is quite remarkable and a game changer. Just reading here. To achieve a Green Star certification, as a minimum, homes will need double glazed windows and doors, air filtration, LED lighting, good access to daylight, renewable energy generation, and no fossil fuel use. that basically means energy generated from gas or coal is basically out the window when Green Star certification is wanted. This future home strategy, and I highlighted in yellow the bits that Passive House already provides. So that again ticks quite a few boxes there already. The future home strategy outline a couple of core elements, which is healthiness. The buildings under the Green Star scheme need to be well ventilated, prevent the growth of mold, build to minimize the entry of pollutants, need to be thermally comfortable. The materials that are need to be low and non-toxic and of high quality lighting, high quality lighting. The buildings need to be resilient and use 40% less water, and they need to have a positive contribution to the environment. Buildings need to be built to generate sufficient renewable energy to power all estimated regulated loads, as well as estimated appliances and plug loads. Basically, use renewable energies for your energy usages. They do not use gas. They need to be minimum 4-star energy rated, battery ready, and they need to have double glazing. Again, all those yellow highlighted items are in the box following the Passive House, basically. Just want to finish the presentation with a couple of quotes of people that have stayed their first time in a Passive House in the Sydney building. I want to say thank you and ask if there are any questions.
Thank you, Timo Bleeker, for that. We have had a lot of questions, and I'm conscious that we're not going to be able to get through all of them. I'm really sorry to say that. But what I've done is a lot of people have asked me questions in the lead up to the event, and a number of questions have come in from members that are based overseas and also in tropical areas. Now, we know that places like Brisbane, where it doesn't get too hot and it doesn't get too cold for most of the year, we know that maybe the cost ratio may not warrant the payback in saved energy for passive houses, and there may not be that appetite there. But we know that different climatic locations require, I suppose, different priorities for passive design. So how do you balance or prioritize against the extremes, those 2-week heat waves versus a 3-week freeze effectively? What's your thoughts on that?
I mean, the passive, when addressing the outer envelope of the building, you basically separate the indoor environment from the outdoor environment. So if you have a 40-degree heat wave outside, or you have 0 degrees outside, doesn't matter too much to the indoor comfort of the building, because the outer envelope addresses that climate. So the insulation basically is thick enough, or the entire wall built up, and the windows are providing that performance to keep the indoor environment at 20 to 25 degrees and related humidity, no matter what the outer climate is.
One of the issues that architects come up with from time to time is the issues with clients' considerations and wishes for what their property, especially in the residential sector, looks like. So we know that sometimes a client might be in a more arid region, but they might desire a more Queensland style property. So that's one issue, I suppose, is sort of tempering client expectations, especially in terms of passive housing. This is a question from John. Now, this is an interesting one. His practice focuses very much on Asian projects. And he's just asked if you could address the passive house concept in an Asian setting, or I suppose a highly tropical setting with, high temperatures, high levels of humidity, and quite often in cities where air quality is very much less than desirable. And sometimes we've seen pollution levels, really escalate in Beijing and Mumbai. What are your thoughts on that?
I mean, passive houses all over the world, we find them in all climate regions, also tropical. So there they address the same thing. When you don't, in the tropical region, if you still want your indoor climate to be at a comfortable relative humidity and that 20 to 25 degrees, this heat recovery system still assists you there, and keeps the humidity outside and the uncomfortable climate situation outside. and the outer envelope assists you to not get the climate, the warmth into the building. So it does the same thing as it does for a building that is in a more cool temperate climate.
Hmm. Another question, and this is in relation to a revised building code. So the questions come in and it says, to what effect would a revised building code have on the demand for passive house buildings? And the viewer makes mention of the fact that Vancouver, New York, and also your hometown, Germany, require construction to passive house standard. What are your thoughts?
Yeah, I mean, if the changes to the NCC would change to be more regulative and more stringent, that would obviously help to get more healthy and comfortable buildings out into the market. Because at the moment, the NCC requirement for airtightness, for example, is 10 air exchanges. So we just learned that 15 air exchanges means 4 minutes. Every 4 minutes, the indoor volume is exchanged. At the moment, at 10. Passive house 1.6. So the better that gets, the healthier and more comfortable our houses will become, and the pressure will go up to actually build and plan those houses. So that would certainly help.
Yeah, okay, great stuff. Thank you, Timo, for that. Another question, and this is more of a comment, but I want your commentary on it. This is from someone who lives down on the Mornington Peninsula here in Victoria. It's a Federation home, well known for lots of leaks and drafts and all those sort of things. It does well in the heat of summer, only needs minimal winter heating, provided that occupants are prepared to accept temperature variations and, like you said, go put on a jumper. And the viewer contends that the Australia's Section J addresses energy efficiency from the wrong standpoint. The lack of ventilation and the limits of glazing will lead to condensation and mold growth. And the closing statement really is that this viewer believes that there will be a lot of sick housing in Australia in years to come. Do you agree?
No, I don't agree, because if you combine all those principles, then you won't get into a situation where you get mold or condensation build up, because the airtightness prevents moisture to get into the structure, for example, and avoiding thermal bridges avoids internal wall temperatures to get that low to condensation mold to appear. Even when having double glazing and the thermally broken frames, condensation and mold on the inside won't appear. They appear when you have single pane glazing and standard aluminium frames quite often, as we have it in our house, yes.
Let's talk about airtightness then in terms of wall systems. So a question from Raphael on the chat, and he says, which wall systems offer the best performance in terms of airtightness? Reverse brick veneer, which is currently used in his build, or is it insulated double brick?
Brick, what was it?
Reverse brick veneer? Yep, or insulated double brick.
It would probably be the insulated double brick. However, it would need to be guaranteed that there are no gaps in the joints of those bricks, and the mortar would need to look up if the mortar is considered airtight. To a degree, yes. It might not be airtight to the 0.6 requirement of passive house.
Okay, thank you. Now a question from Michelle on the chat, and she says, Timo, why is the diagram of your heat recovery system showing a 3-story house with a basement? Is this essential? Very few homes that Michelle knows of have a basement and 2 stories, generally only permitted in residential zonings for freestanding dwellings. Is this only a diagram which has a basement, or is that necessary as such, or is it just a serving suggestion?
Yeah, it's just a diagram. It's not necessary. It can be applied to a 1-story home as well. That system, the magic box, as I called it, can be situated anywhere in the home.
Okay, great stuff.
It can even be situated outside the home, but then the pipework leading to it needs to be insulated.
A question from Misha on the chat as well. She says, is triple glazing and or thermal bridging necessary to achieve a passive house standard in this country?
In Australia, usually double glazing is enough, so we don't need triple glazing. And what was the other element? Sorry, that she said.
I've lost the
Triple
question now.
glazing
Good
and
point. It was triple glazing. Bear with me one second. I'm just going to go back through the questions. I'd already moved on. Sorry. Let's just have a quick look. I'm going to come back to it because thermal bridging. Thanks, Mark. Mark just
thermal
tapped me on the
bridging.
shoulder.
Addressing thermal bridging is an element that under Passive House you need to look at. Usually, when you go for certification, that's to the Passive House certifier to look at the plans and say, I would like to look at this or that detail if it becomes a thermal bridge or if there's a risk there of a thermal bridge. If the planning is already good enough in every detail where there's no concern of a risk, then a thermal bridge assessment doesn't need to be done.
Actually, Misha's clarified. She says thermally broken frames.
Thermally broken frames. Yeah, it's highly advisable. Otherwise, you have a thermal bridge, and mold buildup on the inside face is highly likely.
Let's talk about straw bale walls. This is another question from Rob on the chat, and he says, "Look, do straw bale walls compare? Are they high in insulation properties?"
They can be, yes. It depends on their thickness and how they are put together. It needs to be looked at in a case-by-case basis. Usually the supplier provides technical information, what insulation or how the insulation performance is of that product. We then add that into the PHIPP software and get an outcome of how good this insulates or how it doesn't. But yeah, it's an option.
Okay, thank you. We've had a number of questions from Barbara Reeve on the chat. Barbara, it looks like she's building a house. Thank you, Barbara, for a number of your questions. And I just want to put a couple of them to you, if that's okay, Timo. Barbara, look, she's planning a new home and she wants it to be fully accessible. She has a granny flat out the back, initially 2 studies, plus a fully accessible water closet and shower, plus a kitchenette. Would it be good practice, she asks, to have 2 MHRV systems, one in the granny flat and one in the main home? And the same thing, maybe 2 hot water systems, you know, short runs of pipes and ventilation systems make sense to her, but will they work well? Is that an efficient spend and isn't it efficient design?
Depends a little bit how far these 2 buildings are apart. Generally speaking, yes, I would put 2 units or 1 unit in each building. They can be connected to 1 unit, but any piping that's outside the thermal envelope needs to be insulated properly. Otherwise, you lose that heat energy through that pipe that runs from one building to the other, and the efficiency drops. So you don't get the effect of that energy recycling, and need to add active heating and cooling again. Can be combined, but would need to be looked at a case-to-case basis. That's the same. That's the same for every building.
Okay, great stuff. We may just leave the questions there. What I will say, I'm just conscious of time, but I do want to say as well, Timo, thank you very much for your presentation today. It was really enlightening. We had a huge crowd in, a lot of good chat on the chat box as well. So it was fantastic to spend an hour with you to go through some of the passive house design. So thank you very much for your evident efforts. My final question to you, Timo, if people do want to continue the conversation with you, what's the best way to get in touch with you?
Yeah, they can get in touch with us directly and write to us under the email address that is shown on the last slide, or they give us, they send you the questions to you and you can forward them to us. That's also an option.
Perfect. That sounds great. All right. Well, we'll leave it there. Thank you, Timo Bleeker. I really do appreciate it. We may actually get you back in if that's okay, because the amount of questions and things, and I'm sure there may be a follow-up. So if you have got some time, quite often with all of our popular presenters like yourself, I always try and drag you back in a week or 2 later. So be prepared to get a call from me later to see if we can book you back in for maybe a follow-up Q&A session on more specific things. That is it for today. So thank you very much for... Thank you very much to everybody for joining me today. It's been a really fascinating and interesting session, and thank you so much for your input as well. I will be sending you all an email because there were so many of you on the email session today, on the Zoom call today, that I'll just drop you a quick email afterwards with a link to where Timo's presentation is so you can watch it afterwards as well. I'll also link to our Acumen practice notes on passive house design as well. But that's it for today. I hope you found that interesting, and thanks for spending some time with me. As always, I've been Michael Linke here at the Australian Institute of Architects. Thanks so much for joining me. Until next week on Tuesday at 12 noon, do join me then for another lean-in session. But until then, do take care, stay safe. I'll see you soon. Thanks.